Okay, welcome to the second part of quantum chemistry. This is electron configuration. Let's take a look. The Aufbau principle states that an electron will occupy the lowest possible orbital that is available for it to enter. In other words, electrons don't exist just anywhere around the atom. They must, according to the Aufbau principle, be as low as possible. So the Aufbau principle states that electrons must be present in the atom as low as possible. So how do you determine the order of filling? Simple. Just use this simple remembering device. And here it is. All you have to do is number from 1 to 7, just like this. 1, 2, 3, 4, 5, 6, 7 downwards. Then stagger down 2, 3, 4, 5, 6, 7. Stagger again 3, 4, 5, 6, 7. Stagger one more time 4, 5, 6 will stop there. And then remember the order S, P, D, and then F. S, P, D, and then F. That will tell you the order of filling. And then just use arrows like this. The lowest energy level is the 1s orbital. Go back up, followed by the 2s orbital. Go back up, followed by the 2p, and then the 3s orbital. Go back up, 3p, 4s. Up again, 3d, 4p, 5s. Back up, 4d, 5p, 6x, a couple more times, 4f, 5d, 6p, 7s. Back up, 5f, 6d, 7p, and one more time up, 6f and 7d. Okay? So that's the order of filling. You should also remember that an s sublevel holds 2 electrons. A p sublevel holds 6 electrons, d holds 10, and f holds 14 electrons. So 2, 6, 10, 14. Now those are sublevels, not orbitals, but those will help us to understand how many electrons can be held. Okay, let's go on. Hund's rule. Hund's rule states that orbitals of the same energy level, for example 3p, must each hold 1 electron before a second electron can be assigned. Okay, disregard this. This was a mistake. Okay. For example, let's just say that I have 3 electrons to distribute. I cannot distribute them in this way. 1, 2, 3. Because Hund's rule says that I have to distribute 3 electrons as equally as possible. So I'll put an X through this one because this is not the correct way to distribute those electrons in the boxes. This is the correct way. 1 here, and 1 here. Because again, Hund's rule says that electrons must be distributed evenly in these boxes. So I can't have a second electron until each one of these boxes has 1 electron. Finally, the Pauli exclusion principle. And the Pauli exclusion principle says this. It states that no 2 electrons in the same orbital can have the same spin. So if you have an electron that's going in this direction and you have another electron that's going in this direction, that's okay, that's all right in a single orbital. But you cannot have, according to the Pauli exclusion principle, 2 electrons moving in the same direction. So that's the Pauli exclusion principle. Okay. Next. Magnesium in the excited state might have the electron configuration 1s2, 2s2, 2p6, 3s1, 3p1. Notice on this 3s1 that the electron, which could have been held in the 3s orbital, has been moved up to the 3p orbital, so that the excited electron has absorbed energy. It's absorbed energy and has jumped from 3s to the 3p orbital, from the 3s to the 3p orbital. But don't worry, it will eventually emit energy in the form of a photon and fall back down to ground state. It will fall back down to ground state. Let's talk about noble gas configuration. In noble gas configuration, we use electron configuration of the previous noble gas in brackets, followed by electron configurations for the energy level being filled. For example, bromine. We're going to start with argon and place that in brackets. Argon has, let me check a periodic table. Argon has 18 electrons. So simply by writing AR right here in brackets, I'm really indicating 18 electrons, right? So 18 electrons there. Then after those 18 electrons are distributed, The next orbital is the 4s orbital. That holds 2 electrons. The next one is the 3d. That holds 10. All d's hold 10 electrons total. And the next is 4p. Now p holds 6, but I don't need 6. All I need is 5. So I can write the noble gas configuration like this. AR in brackets, 4s2, 3d10, 4p5. Okay? Just like that. All right. So let's take a look at some electron configurations. Helium, simple. Look on your chart. 1s is the lowest energy level. It can hold 2 electrons, so 1s2. What about lithium? 1s2, 2s1, 3 total electrons. So it's going to be 1s2, 2s1. Boron, 1s2, 2s2, 2p1. That's a total of 5 electrons. Aluminum, 1s2, 2s2, 2p6, 3s2, and then 3p1. Notice this is a total of 13 electrons for aluminum, right? I'm just going from the lowest energy level to the highest energy level. Magnesium, 1s2, 2s2, 2p6, 3s2. That's a total of 12 electrons for magnesium. Just going on my chart from the lowest to the highest. Germanium, this is a long one. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p2. That's germanium. Lowest to highest, remember S's hold 2, P sublevels hold 6, and D sublevels hold 10. Barium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, D's hold 10, 4p6, 5s2, 4d10, 5p6, and 6s2. That's barium. That's 56 electrons. Count the superscripts. They'll tell you what the element is if you don't know. So if you're given a electron configuration, count up superscripts and they'll tell you what the element is. Calcium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. That's a total of 10, 20 electrons. Fluorine, 1s2, 2s2, 2p5 for fluorine. Nitrogen, 1s2, 2s2, 2p3. Oxygen, 1s2, 2s2, 2p4. All right? 1s2, 2s2, 2p4 for oxygen. All right, let's talk a little bit about orbital box diagrams. Orbital box diagrams are boxes that are used to represent atomic orbitals, and arrows are used to represent electrons. For example, let's take a look at the orbital box diagram for magnesium. I'm sorry, let's start with carbon. Now carbon has 6 electrons. The lowest energy level is the 1s orbital, so we'll start down there. So 1s, then we go to 2s, that's the next higher one. We'll put 2 electrons here of the 6 and 2 more there, and then we have to distribute the 2 remaining ones in this 2p sublevel. 2px, 2py, and 2pz. Now, notice that the electrons cannot go in the same orbital because Hund's rule says you must distribute these evenly before you put a second one in. All of the boxes must have 1 and this one doesn't have 1. So we say this is 1s2, 2s2, 2p2, and these 2 electrons go in this orbital and this orbital. So that's carbon. Magnesium. Magnesium has 12 electrons. And so its orbital diagram would look something like this. 1s, just like the 1s for carbon, 1s, 2 electrons go down there, then 2s, a little higher energy level, so we'll draw it a little higher. 2p, 6 electrons there, 1, 2, 3, 4, 5, 6 for 2p, right? And then finally 3s, 1 electron up, 1 electron down. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons for magnesium. 12 electrons for magnesium, okay? All right. I'm going to let you work on this one. This is the, I want you to just make up an element and you draw the electron configurations for a couple of different elements. You choose the elements and use this page then to make up a couple of orbital configurations. All right, let's go to the next page. It says, there are 7 main electron clouds which surround the nucleus of the atom. 7. These are areas where the electron is most likely to reside and is denoted by the symbol N. Is denoted by the symbol N. So if you look at a nucleus, if this is the nucleus, I'm just going to draw a part of the orbitals, n equal 1, n equal 2, n equal 3, or sublevels, I'm sorry. This is main energy level 1, main energy level 2, main energy level 3, 4, 5, 6, and 7. So 7 main energy levels maximum. We really just talk about the first 1, 2, 3, 4, but it can go as high as 7. Each of these energy levels has one or more S sublevels, right? Because S sublevels are the lowest energy. So all of them have an S sublevel. So each of these main energy levels has one or more sublevels. N equal 1, or ground state, has one sublevel called the S sublevel. N equal 2, 2 sublevels. That's easy enough. Called S and P sublevels. N equal 3 has 3 sublevels called S, P, and D sublevels. N equal 4 has 4 sublevels called S, P, D, and F sublevels. And it keeps going, but that's as far as we need to know. Okay? So the number of the main energy level tells you the number of sublevels within that main energy level. Again, one sublevel in N equal 1, 2 sublevels in N equal 2, 3 sublevels in N equal 3, and 4 sublevels in N equal 4. And they are S, S and P, SP and D, SP, D, and F respectively. Okay? All right, next page. Within each sublevel, there are one or more orbitals, right? Within each sublevel, there are one or more orbitals. In S sublevel, there's one orbital. In the P sublevel, there are 3 orbitals. In the D sublevel, there are 5 orbitals, and in the F sublevel, there are 7 orbitals. So you just have to memorize those numbers. SPDF 1, 3, 5, 7. SPDF 1, 3, 5, 7 orbitals respectively. Now, any orbital contained within any sublevel within any of the main energy levels, remember there's 7, can hold a maximum of 2 electrons. Now let's not get sublevels and orbitals confused. Sublevels are S, P, D, and F, but the S sublevel has 1 orbital, P sublevel has 3, D has 5, and F has 7. Each one of these orbitals can hold 2 electrons. So an S sublevel can hold 1 times 2, or 2 electrons. A P sublevel can hold 3 times 2, or 6 electrons. A D can hold 5 times 2, or 10 electrons, and an F can hold 7 times 2, or 14 electrons. 14 electrons. Now, the order of sublevels in any main energy level in terms of their energy is this. S is the lowest, followed by P, followed by D, followed by F. So it's S, P, D, and then F. Okay? All right, let's move on. Electron configurations use superscripts. They use superscripts to denote how many electrons are found in each sublevel. For example, chlorine has 17 electrons, and so its electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p5. If you're given an electron configuration and wish to know what the element is, just count the superscripts all up. So for example, if I have 1s2, 2s2, 2p6, 3s2, 3p6, 3s2, add those up, that comes out to 20 electrons, must be calcium, Now remember that if an electron encounters energy, it might absorb that energy and move up to a higher energy level. This is said to be excited. So once an electron moves into a higher energy level, it's called excited. All right, let's talk about the electron configurations then of ions, all right, of ions. Let's take calcium ion. Now remember, calcium is in the second column. That means it wants to lose 2 electrons, and when it does, it becomes Ca2+. It's lost 2 electrons, so it no longer has 20 electrons, it has only 18. So here they are, 1s2, 2s2, 2p6, 3s2, 3p6. Let's count those up again. 2 plus 2 is 4, plus 2 plus 6 is 10, plus 2 is 12, plus 6 is 18. Fluorine ions. Fluorine ions want to gain 1 electron to become F-1 because they're in that 7th column. So when they do that, they become 1s2, 2s2, 2p6, 3s, not 1, but 2. So fluorine ion is going to have not 11 electrons, but, excuse me, not, yes, 11 electrons, but 12 electrons, okay? Magnesium ions, they're like beryllium and calcium. They want to lose 2 electrons, and when they do, they become 1s2, or magnesium becomes 1s2, 2s2, 2p6. Remember, magnesium had 12 electrons originally, but it lost 2 and becomes 1s2, 2s2, 2p6. It lost the last 2 electrons. Aluminum, Al3+, right? It's in the third column under boron. It's going to be Al3+, so we have 1s2, 2s2, 2p6. Oxygen, 1s2, 2s2, 2p6, because it gains 2 electrons. Now, noble gas configuration. To do noble gas configuration, we go to the previous noble gas, antimony. The noble gas previous to that is kryptons. So just by writing Kr in brackets like that, we're taking on those electrons. There's a total of 51 electrons, but we're only going to worry with krypton of the first electrons. So krypton takes care of those initial electrons, and now we're in the outer shells. After krypton, we get 5s2, 4d10, 5p3. Those are the last electrons in krypton, and excuse me, in antimony. Next is arsenic. Arsenic, the previous noble gas is argon. All right, so we take care of the initial electrons just by writing that bracket. Then we have 4s2. After those initial ones, we have 4s2, 3b10, 4p3. And then niobium. Use krypton, the previous noble gas, to take care of those initial electrons. Then after that, we have 5s2, 4d2. Skip this protactinium. It's too large an atom. We'll just skip it, okay? All right. Next, incredibly, the periodic table can be used to make the task of writing electron configurations much easier. If you look at the the periodic table, you can divide it into 4 blocks: S, P, D, and F block. Okay. So notice there are 7 rows on the periodic table, and that's just like the number of main energy levels. And also notice that there are 2 columns in the S block, which is the same number of electrons which an S sublevel holds. So these atoms right here in the S block are elements whose last electron is in an S sublevel. These ones, last electron in a P sublevel, D sublevel, F sublevel. All right, last one. Last page. There are 6 columns in the P block, which is the same number of electrons held in the P sublevel. There are 10 columns in the D block, which just happens to be the number of electrons in the D sublevel. And finally, there are 14 columns in the F block, which is the exact number of electrons in an F subshell. Folks, that concludes the second part of quantum chemistry, and I'll see you on the next one. Thank you.